All right, so let's spend a little bit of time talking about multi-step synthesis and combining some of the reactions from this chapter with the chapter on alkanes. And this is kind of what we're going to be doing from now on when we add new reactions and new functional groups is using them as tools. And like a typical toolbox, we don't always use the same or all of the tools. We just use the ones that get the job done. So let's just kind of start with a previous unit. So what can we do with alkanes? Well, pretty much the only reaction we can do is to make them haloalkanes by doing a free radical substitution. And so again, that's like typically the only thing that we can do with alkanes. And then we did a lot with haloalkanes, as we saw in one of the previous units when we talked about elimination and substitution. We could do a nucleophilic substitution to get other functional groups. So we would replace that halogen with a nucleophile to other functional groups on there. Or on the flip side of that unit, we could do a beta elimination to make an alkene. And that's kind of where we're at this chapter now, because we can take that alkene and do like an electrophilic addition of, say, like HX and make a haloalkane. We did some reactions where we took alkenes and did some electrophilic additions. Like with OH or 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 even amines, and make other functional groups out of that alkene. And we also could go back to an alkane by doing a catalytic hydrogenation. So there are a variety of things that we can do and a variety of different pathways that we can take. So let's look at a couple examples. And I want to kind of, with the first one, demonstrate some cool things that we can do. So this is like a little trick. It's kind of a cool trick where we can move a pi bond or a leaving group around. So for example, if we want to do this transformation, and put a bromine there, we can't do this in one step. Because if we just add, if we try to do, let's say, fix that here, do a free radical halogenation, where is that bromine going to go? It's going to go where I can form the most stable radical, which on this substrate is a tertiary position. Okay, so that's the only thing we can do to put a leaving group on there. That's the only thing we can do with an alkane. So we're kind of stuck in terms of a variety of reactions. So there's only one reaction we can do, and this is it. Well, let's see about putting something on where we can get that bromine to move around. So if we do an elimination, a Zy-Steph elimination, we can put a double bond there. So pick a strong base, sodium hydride. You could probably use, like any strong base, that would give you a Zy-Steph elimination. Now, notice that we have tactics from this past unit about putting a bromine on that position. We talked about doing an anti-Markovnikov's addition using HBr and peroxides. And if you look at what we've done, we've pretty much, quote unquote, moved that bromine around. Then we could do another elimination to put an alkene there. And we just got to be kind of careful about the base that we choose because we want to do a Hoffman elimination. So we need a bulky base, like tert butoxide, um, or you could use DBU or some of those other ones that we talked about. And notice again, we've moved something around. We moved a pi bond around. Now, if we were able to do another anti-Markovnikov's addition of HBr, that would put the bromine on the end. So this is just kind of a tactic when we think that we have to move a group around. We basically add something, take it away, add it back with a different regiochemistry, take it away until we get to where we want to move it. Now let's look at another example. Okay, so we want to get from this cyclohexane to this dialdehyde. And what I want you to do is think about all the reactions of all the reactions we talked about. What are the ones where we've gotten carbonyls out of them? At this point in time, we've only talked about one reaction that is capable of doing this. The only reaction that can form carbonyls is ozonolysis. That's the only one. No, we'll talk about more later, but right now we'll make it easy on ourselves. That's the only tool we have in our toolbox right now to make carbonyls. And what do we have to start with in order to do an ozonolysis? You have to start with an alkene. So if I work my way backwards, what is that alkene going to look like? Well, let's talk about going backwards in an ozonolysis. So I'm going to number these carbons here. 1, 2, 3, 4, 5, and 6. Now to go backwards, I'm going to imagine um, removing these oxygens, and I'm going to connect the carbons to each other with a double bond. So I'm going to connect carbon number 1 to carbon number 6 here. So here's 1, here's 6, and I'm going to connect them with a double bond. And there's 2, 3, 4, and 5. And actually, I should have drawn that down here. There we go. And I'm just going to put down the conditions for an ozonolysis. Now, have we talked about any reactions that can do this? Go straight from an alkane to an alkene. No, and there's none that really exist that can do that. Right? Remember, the only thing that we can really do with an alkane is put a halogen on it. So let's do that. Since all the carbons are the same of this cycloalkane, doesn't matter where the bromine goes, it's always the same. And then do we know how to get rid of that bromine and make a double bond? Yeah, we spend part of a whole unit on beta elimination. If we use a strong enough base, we can do an E2. And in this case, as long as it's a strong base, doesn't matter if it's bulky or not. There's only one place that double bond can go, and that's where we need it to. All right, so notice how we're combining reactions from multiple units with these multi-step synthesis. So let's do one more. So we're going to start with this alkene. And we're going to go to this product. And then we do end up with the enantiomer, but let's just kind of focus on getting to this here. So what you want to ask yourself is, how do I know any way to put two OH groups anti to each other? So we learned that we can do an anti-dihydroxylation, but what do we need to start with? We have to start with an alkene. So I'm kind of working backwards here. I know that in order to do this, I have to start with an alkene where the OH groups end up across the double bond. Now I want you to compare this alkene that I drew in black and our starting alkene. Okay, so notice I got the double bond there and it's moved there. Remember the trick that we did? How do we, move a double bond? Well, maybe we put something on here, like a bromine, add something across the double bromine by using HX or HBr. And all this is an elimination. Now the question is, what kind of base should I use? I know I need to use a strong base because I want to do E2. So, but is this the Zeisteff elimination I want or the Hoffman elimination? That's the more substituted alkene. If I did a Hoffman elimination, I'd go back to where I started. So this would do, if I tried to do an elimination, that would be the Hoffman elimination. So I'm just going to use a small, strong base. I could use sodium hydride. It's tertiary, so KOH would work well as well, but NaH, KOH, those will work just fine. Just nothing bulky. And then the last trick is remembering, well, how do I do an anti-dihydroxylation? So that's a two-step process where the first step is I make an epoxide out of that alkene. So doing that first step will get me here. And then the second step, I do an acid catalyzed ring opening. All right, so notice the kind of first important foundation is knowing your reactions. This multi-step synthesis is impossible if you don't know what tools are in your toolbox. You can't know what how to put a whole project together. So knowing the individual reactions is key. And if you're having issues with those, then you need to shore those up first before you do anything else, before you even try these. But you're only going to get this right by doing problems like these over and over again.